Okay, so I've been actually pretty excited to do a stream like this one for a long time now. Actually, I would say years. Actually, it's not like just weeks. Um, so if you ask a lot of people like in the more like academic side of machine learning, like what do industry people not do more of? Often like what people communicate is causality. So people just don't use causality enough. Like the idea is that most machine learning algorithms work based off of correlations, but it's very hard to figure out like what caused what. Unfortunately, though, like whenever I actually not whenever. Uh, yeah, so more so just so everyone knows, like we may have like a maintainer of the causal inference library join us later today. Hey Oda, nice to see you on stream. So whenever I try to get into causality, the first thing the book that everyone recommends is this one. So this is the book by the Turing Award winner Yuria Pearl. Um, I like the book is good in terms of like it does explain quite a bit of history, like why these ideas are important and the proofs. And a lot of people in the community actually really like this book. I personally did not enjoy it all that much, not because it's a bad book per se, but it sort of like assumes that this stuff is useful, and it didn't give me a sense of how I could actually use it at work. And so this sort of changed when I picked up this other book. So this is an amazing book. I'd recommend anyone who does anything with machine learning or data to buy this book. So this is a book by Richard McElreath about just statistical rethinking and Bayesian thinking. But what I really loved about this book is that he discusses all of these techniques from a computational perspective. As in, you're some programmer working with data, and you thank you for the new subscription. I appreciate a floral system. That does sound like formal system. That was actually my old name before Antis for Mark Seraphim. Oh, subscribe to Prime as well. Thank you so much. I appreciate it. Uh, so again, so what I was hoping to do today, excellent. Yeah, it's really nice to have you on, Floral. So what I was hoping so what I was hoping to cover today was give you sort of a very brief perspective as to like what does like how you can represent probability distributions as graphs, like what are sort of the main things that people think about. And then I really want to make this as much as possible about like a real library. So in this case, we're going to be using the Causal Inference library by Moritz Schauer. I believe that's how you pronounce his name. Um, and we're gonna be covering causal inference in the Julia language, just because I've definitely noticed that in Julia people tend to have a lot of these nice scientific libraries. But again, before we go into the details, let me just give you some sense of like why this stuff is important and how it all works together. So let's just do that. All right. So I'm gonna go to this whiteboard here. And so the first thing I want you to think about is like this is something that people cover in sort of like machine learning classes. Actually, before deep learning, like this is how people would sort of cover machine learning. Like they cover this idea of DAGs. Uh, so let's say I'm gonna have a DAG like is it gonna rain? Yes or no. And then my decision should be like I don't know, umbrella, yes or no. Actually, wait. Let's do. I think let's just do an immediately more useful example because I found a better one. Yeah, let's just forget this part for a sec. Okay. So there was one example I already liked here. I'm just gonna borrow the same one here. So yeah. So let's assume, for example, that we're trying to study like the likelihood that someone has some sort of cardiovascular disease, right? Uh, and so like you're a doctor, right? So what you're basically gonna do is you're gonna ask like your patient all sorts of questions. Like you may ask them, for example, do you have a respiratory disease, for example? Let's say like respiratory disease, like let's say asthma, respiratory disease, right? And another one could be like, well, like, do they have like for example, like are they obese? So these are two factors that are like highly correlated with cardiovascular disease. So this is a graph, and it's called a DAG, which stands for like directed uh, acyclic graph. Uh, Directed means there's arrows. Acyclic means there's no cycles, so you can't like have an arrow that goes back like this. Uh, and like you could have something that causes something else, like maybe cardiovascular disease will make you more likely to get a respiratory disease, but we're just not gonna like we're just not gonna cover those kinds of DAGs right now. And it's a graph, well, just because there's nodes and edges, so that's just like the basic structure of a graph. So typically, like let's sort of encode these as some probably like as mathematical variables instead of like text here. So cardiovascular disease could be C. We call this C. This is O, and then this is R, right? And so basically what you're generally doing in a lot of probabilistic modeling is you're learning some sort of probability distribution P over R and C, right? So this is sort of like what you're learning. But the nice thing about this problem is that we can simplify it because we know that cardiovascular diseases depends on obesity and probability of respiratory disease. So then this becomes, we can make this more tractable by then saying, well, the probability of a, right. So we'll say the probability of a cardiovascular disease, given that you have obesity or a respiratory disease, uh, times the probability of obesity times the probability of a respiratory disease. So these are called like in general like just priors, and then this is a conditional likelihood because like given that you have these, how likely are you to have this? This is why it's called a conditional probability, and this one is called a marginal likelihood. So this example actually is a fairly tricky one, even though it's just like 3 nodes, because it has like a concept called a collider. So a collider is basically when you have two effects coming influencing the same random variable. Uh, and so the question then is like, well, given that I know that you have a cardiovascular disease, do you have obesity or respiratory disease? And this becomes very tricky because you're not actually sure which of the two is more likely. But let's say again, like, well, if I know that you don't have a respiratory disease and I know that you have cardiovascular disease, then it's very likely that you're obese, for example, unless there's some other stuff that's missing. So this brings us to our second source of bias in these models. So one is collider bias, and then the other one is called confounding variables. So let's say we want to have something like what was the graph that you like weight gain activity level 8. Okay, so we know, for example, that your activity level determines your weight. So there's some sort of causal relationship here. Sorry, some sort of correlation here. But turns out, what we actually do is we start telling people like, hey, well, you should exercise more. And then a bunch of people exercise more, and then turns out they don't actually lose weight. So then you may think like, oh, well, actually there isn't a relationship here. Or there is basically a third hidden relationship, which is called a confounding variable called age, where your activity level, your age determines your activity level, which then determines your weight, or your activity level determines, like, gives us a good guess for what your age should be, and then your age is really the main thing that's responsible for your weight. And so this is important because while you can give people advice to be more active, you can't tell them like become younger. Like this is non-actionable, non-useful advice. And so it's always important whenever you're doing an intervention, like as in like so now for example, let's say the goal is to reduce weight, and you're doing an intervention like changing activity level. The question is, does this change weight? So the interesting thing is, even though like we do quite a bit with statistics already, we don't actually have a good way of answering these questions with traditional statistics, which is why like Pearl in his book like introduces something called the do calculus, which is you make an intervention, and then you observe the effect, and this lets you um, this lets you figure out like the impact of something and better understand like the causal structure. Um, so there's one last thing. We can have a bunch more graphs, right? Like, what? Let's say, like in this case, for example, this is interesting. Well, like your age, for example, influences your activity level, but it also influences your weight. Let's say this was the DAG that we wrote. This also seems to make sense, right? And then, so this means now if there's like some sort of hidden relationship here, and if you don't, so if you know the age, then you can compute the conditional likelihoods of each of these. But if you don't know the age, then you're not really sure if there's sort of a hidden arrow here. But in all cases, this effect, I'm not sure if it has a name, but it's basically like one thing can have two causes. And it's just sort of important to mention. So the last thing I want to show you is this concept of deseparation. So here, I thought this was an amazing lecture note. It's like it's sort. I think it's like a TA at MIT. I think I'm pretty sure she's a PhD student there at this point. I forget though. So let's say we have a DAG that looks like this, right? And so the question is, like first off, let's remember why we're doing this in the first place, right? Like we're gonna have A, and we're gonna have C, and we're gonna have B, and then let's say D, F, and then G, and then here we have E, right? So the question here is, uh, are A and B conditionally independent given D and F? Okay, so what this is basically asking is if we know D and F, is there uh like basically this is asking, let's put it in algebra. So it's asking that if P of A given BDF is equal to P of A given DF. So you see, like these two terms are the same, but here we've dropped the B. And so this is basically saying if we know that D and F are true, knowing B doesn't give us any additional information. So this doesn't seem trivial to figure out, but this concept of conditional independence is super important. Like the main idea, like I would say the simplest way to reason through conditional independence. Oh, yeah. So the simplest way to reason through conditional independence is this. Like let's say you have something like your age determines like your like breathing, which determines your like cardiovascular disease. So let's say this is the DAG that we're working with, right? So the idea of conditional independence, so like what each one, let's say this is age, this is breathing, and then this is C. So probability of A, let's say, in general, this is the marginal likelihood that we're working with. But now let's say we want P of C, right? Like if we want P of C, then uh, given B, this is equal to P of C given BA, right? Because we know that this is true, so we don't care what the age is, so we do this. This is not generally true if there's some sort of like hidden, other graph here, or if there's like some other confounding variables. But this is the idea. We are building a model of the world, and it's very likely that the models can be wrong, but it gives you a good framework to think about these problems. Um, so the reason I was mentioning this thing before is okay. So we're asking like let's say we know DNF, right? And so we know DNF, and we want to figure out if A and B are conditionally independent. So the way we do this is there's actually an algorithm to do this. And so the first one is you draw the ancestor graph. So basically, you remove all of the non-ancestors of uh, of this graph. So here we're going to come in and we're going to erase this thing and we're going to erase this thing. So then we're going to do this operation called moralize, which is basically any two nodes that have a common children, we draw an edge between them. And then we make all of the edges undirected. So we just remove the lines. So this is what our new graph looks like. And then we delete the givens. So we delete the information that we have DNF. And basically, because A and B are connected here, they are not in fact going to be conditionally independent given DNF. So again, remember like it's an algorithm. So basically so this idea of deseparation is a generalization of conditional independence, and it has three steps, right? So the first is you come in and you delete non-parents of the givens. Then you make undirected. You make parents of same children connected. And then you delete givens. If uh, if two remaining sets are connected, they are not conditionally independent. And if they're not connected, then they are in fact conditionally dependent. So, you may think like, oh, like, this sounds like a mechanistic process. Like, why can't we have like some sort of code that does this for us? And in fact, we do. Like, that is part of what causal inference does. So I think like now that we've sort of covered all the basic theory and what like 15 minutes we've covered causality, like I'm sure some Bayesian professor is gonna yell at me for this being really imprecise. Um, but this is good because like we can actually just like move on to code right now. So what I'm doing is I'm going to be running this in Julia, and so I already have this set up here, like with the Windows subsystem for Linux. And so I went to my directory here, and I'm gonna say uh, first off, like okay, so I'm in the proper directory. I'm gonna run Julia. All right, so then I'm gonna go to the package manager, and then I'm gonna say activate causality. So this is sort of like the pip environments, right? So then I'm gonna say add Pluto. It should already be added, if I'm not mistaken, unless there's an update to Pluto. Hey, to everyone in chat, like feel free to ask me any questions. We're gonna be doing like applied like causality frameworks. I went through all the theory already, but if you have any questions about confounders, collider bias, uh, non-identifiable causes, one thing causes two things, and how to model probability distribution as a graph, please let me know. So yeah, so we're gonna also add causal inference. Let me just make sure that this is actually the proper way it's called. I believe it is. Okay, no changes. Excellent. So, okay, so now we can go back and we can say using Pluto. So Pluto is a reactive notebook that lets you do. It looks a lot like Jupyter, but it's reactive, as in when you update a cell, it updates all its dependent cells, and I've been enjoying it way more than other similar alternatives. So this is an old command to run Pluto. So now, okay, you just say Pluto run, and then you say port. Okay, I see. So Pluto.run, and then I'm just gonna run. Okay, so we're gonna create a new notebook. Okay, so before we start talking, like, let me be clear what I mean by applied causality. For me, uh, applied causality uh, means basic like so. This is what I call it, but what someone like Moritz would call it, they would call it causal discovery. So what that means is that given some data set, like right, like we have a data set that looks typically like this, like you have a label, and then you have feature 1, x1, x2, x3, x4, x5. And typically, like, if you've watched like a bunch of my streams, in when we say it, like in machine learning, really the core framework is given this vector x, right? We want to be able to figure out the label. So this is supervised learning. So notice that we're not talking about these inner relationships. We're not talking about what caused what. Like, they're just features, and we just take them all in, and then we make some sort of prediction. So instead, what we're gonna do is we want to take in a data set like this, and then we want to figure out the DAG for it, right? And this is interesting because after you collect a bunch of data, you collect a DAG, and let's say, like, this is something for medical diagnosis, you can get some better sense of like what could cause what, which things are very related to each other, which things are like not likely to be related to each other. And as you get more and more data, this whole thing starts to make a lot more sense. And to me, like, this is extremely valuable, like, because this turns causality from something that like a couple of academics with really expert knowledge in causality can do to something that pretty much everyone can do. Like, like the idea is you can just load a data frame or a CSV, and then you start doing this sort of causal analysis, and that's exactly what I want to be doing today. All right, so let's get started. So first off, we're gonna go here. So I'm only going to be doing stuff in Pluto because it makes it more easier to say stuff interactively. But let's say, okay, we're going to say using causal inference. And then using light graphs. So this is this is a library to do plot DAG, plot DAG, plot DAG. Where's plot DAG? Oh, I see. Yeah, so let's make sure we also install this here. So what we're gonna do. Okay, why is this taking so long? Is it crying here? Okay, so it wants us to import package. Okay, that's fine. So we're gonna need to make sure that we also include this. And so we're running it from which directory? From causality experiments. And then I also believe I did have I had git cloned the project earlier, so it's like here, git examples. And then yeah, so I want to say I mean, let's see if I do this. So if I say uh include uh and then plotdag.jl. All right, does this work? Okay, we'll figure this out. I think the other ones look like they'd be simpler to solve. So let's say we import package, right? And then package dot add light graphs. Light graphs is not defined. Okay. Okay, so using light graphs. So maybe I want to say just import light graphs, right? Is this working? Okay, so if I say import light graphs, why is this so buggy today? let's see. So using causal inference, because I did add them to my project toml, I believe. I mean, yeah, I did. Yeah, I mean, I guess I'll just use. I mean, I can just default back to Visual Studio Code, so this is fine. Slightly disappointing, but fine. Yeah. So what we're gonna do is, so I'm gonna stop Pluto. All right. So now I'm here, and so now I'm gonna say code dot, and so this is nice because it lets me open up my local VS Code to this like remote service that's running Linux, which is happens to also be running on my machine. But yeah, so we're gonna say activate causality. Actually, sorry, Julia, activate causality. Oh, actually, yeah. So activate causality. It should already be activated. Okay, excellent. So now we can get out of here. And so let's start doing this, right? So we're gonna come into this. Yeah. So first off, we're gonna say we're gonna be using causal inference. Let's go here. Okay, and then using light graphs. And then we're gonna include causal inference.jl dash examples dash plot dag.jl. Right, so let's see. So now we're gonna say n is equal to 1000, p is equal to 0.01. I'll explain what all of these variables mean in a second. And then this is random number n. Let's just do sanity check, make sure this is running just fine. Test. Julia is sort of slow to compile initially, but after that it gets really fast. Okay, so it's saying our package light graphs not found in current path, like run import package add light graphs. Do I not have light graphs? Oh, I do not have light graphs. Okay, well, that is okay. So I'm gonna say so activate causality, and then I'm gonna say add light graphs. And so this is really nice. It should just add it here. Yeah. So this is sort of like in Python, this is sort of similar to the pip freeze command, where you can do this sort of stuff really quickly and easily. Let me just make the font a bit smaller. Anyway, yeah. So now if we come back here, this should now work fine, right? Like, so if I come back and I go Julia test GL, light graphs is again not found in the current path, but it is in the current path. Wait, so should I run it directly from the shell? Julia run file from roughly. It's taking forever to crash. Why is this so slow? That's why I really like the. I mean, let's maybe do this. All right, then say test. If I say include. Oh, interesting. So test.jl. Yeah, the compile times could definitely use somewhere. It makes it a bit annoying to debug these like really basic stuff. Anyway, while this is doing its thing, let me just show you the graph that Moritz had in the examples. So where was it? Here. Okay. It'll be simpler if I also show it to you on the whiteboard. So basically, like, okay, uh, so we have these variables n and p. Then we have x, which is a random variable from n. So it's a number from 0 to 1,000. So we have basically x. So then we have this thing called v, and v has something coming in from x plus this other random number. And then w is also coming in from x. So it looks like this. And then the z is something v plus w plus some other stuff. So z. And then we have this thing called s. And then indeed, if you keep going down, this is like what this graph looks like. What's interesting about the output here is that you see here this dot. Like this basically means that like the algorithm can't figure out if it's x causing v or if it's v causing two things, z and x. Um, but you know, like if you could always like add some of your domain knowledge to sort of figure this out. But the nice thing is that you know we put the code in here, and then we basically said, okay, well, we want this data set, and we put everything in like its own tuple. And then after you run this algorithm, and then where was this, the Gaussian test? Yeah. So after you run this algorithm, and then you can plot and figure out what all the relationships are, and then you can plot, and then you can just like plot the DAG. And so here, like, yeah, it shows like plot the DAG, and then and then give it the keys, so it has its names, and then you just save it to PDF, which you can then take a look at. Is this done? Okay, so we didn't add TXZ graphs either. Let's do that. All right, and so now we can go back, and then we can do the same thing and include test.jl. Okay, so now we have to add TXZ pictures. Okay, now to go back, include test.jl. Okay, interesting, right? So now that what this is doing is it's showing us the like the 1,000 element array here. So this is like, it looks like what random of 1,000 does is that makes 1,000 samples. So yeah, like you can already see this sort of working. So I'm just gonna maybe we should add using 60. I mean, is this mentioned in plot.dag? Because then I'll just commit them for him. Oh yeah, they are. How come this didn't? I mean, they are explicitly mentioned though. Okay, this is good. So now what we want to do is, okay, so we're saying we want to take here, like, where was it? So we're gonna be doing 1,000 samples, and then let's just draw this causal diagram. So we're gonna have v is equal to x plus. Let me just remove this. So we're mostly coding now. Okay, so yeah, so we're gonna do random n times 0.25. And then we're going to say w is equal to x plus rand n times 0.25. And then z is equal to v plus w plus random of n times 0.25. And then we're going to say s is equal to z plus rand n of n times 0.25. Set up the data frame. I'm just doing this by hand because I want to be doing this for some real data soon, so I get used to it. Equals z, and then s equals s. And then we're going to say print line, running some Gaussian tests. So let's just have a short to do for ourselves. Like, what is this PC-alg test? Nice thing is we can actually just take a look at the source code here. So they're going to time it. Like, this is like Julia has like some really nice decorators like this for just like perf monitoring. PC-alg, DFP, and then it's called Gauss psi test, and then variables is equal to so we're just basically doing like array comprehensions like in Python for key and keys of df. Because yeah, that's why I like Julia. It's like if you know some Python, it's not like crazy to figure out what this rest of the stuff means. So then we're saying plot dag and then sg with variables, and then we're gonna come in and save to a PDF this est dag, and then give it let's see, and then we'll figure out what this TP stuff is. Save, yes. So now what happens if you do this? Okay, so now we want to add z. Why? Z is not found in project or manifest or registry. Am I typing it right? Um, I think this will work fine. Let's try this. So not found in current path. I wonder if it's Tixie plots or Tixie graphs. Oh, interesting. Um, I mean, yeah, let's try both actually. Like Tixie plots. Okay, this is doing something. This is very weird because if you look at the here, it has graphs, it has pictures. So what is it that needs to exist exactly? I wish this would tell me where. I mean, I'm suspecting it's here, like probably this line, right? Using make heap. So I mean, what happens if like if I just print this, what's gonna happen? Oh, huh? Does this also use TXT? Like using TXT graphs, using TXT pictures. Oh, I see, I see, I see. Oh, yeah, yeah, okay. TXT graphs, using TXT. Uh, yeah, thank you, Moritz. I think this should fix this. So now let's uncomment this. Okay, success. Something's happening. So load error, undefined variable not found. Which one? Okay, so we have df, we have p. This is very weird sometimes. Like it's just like where's the error? An expression starting line 27. Oh, I see. ESTG. What the hell is variable? Oh, variables. I see. Okay, something happened. Uh, draw rounded corners. Oh, interesting. I see. So you just straight up get all the LaTeX there. Okay, this is good. And so I think we were just missing the one line from here. Where was it? You are the first entry, by the way, for causal inference, Moritz. Like if you put Julia, um, so I think this was the only thing that was left, right? So if we come in and we say this, now this should work. Wait, what happened? Could not spawn Lua LaTeX. Uh, oh, interesting. Is there like typically when you work with this stuff, like do you have LaTeX pre-installed, or just like can you run some Julia command and then just gets to you the binaries? Because I've mostly been using Overleaf for any sort of LaTeX document. Julia error. Lua LaTeX. Yeah, it's okay. Like I think that it's just in general. I know Julia is pretty good at getting binaries with the package, so I wonder if there's just like. But I would check out tick plots for dependencies. Oh, that is a good idea. Actually, tick plots. Hmm. Let's see. I mean, I wonder, this may be really hacky, but just as a way to get by. No, but view. Oh, okay, interesting. Yeah, let me grab that. Take the grass. Oh, Julia type. I'm just gonna check it from my laptop next to me.
If I get too.
Okay. So okay, we're saying take the graphs, dot plot. I mean, yeah, can I just do that then? Take the this work. Yeah, these packages look like they're changing because it's saying it doesn't have a method plot. Oh, on a TXZ picture, I see. Um. Oh, but maybe if I do this then. It is saving the tech for some reason though. I wonder why it's doing that. Return false. And picture. Huh? This is, oh, it has like an error. It's saying something about draw around the corner. Yeah, this is not the graph we were plotting actually. It's something else entirely. Okay, so let's see. I mean, I guess like also, let's see. So in the meantime, I guess like what we can do though is like just make this, keep it as is, and then let me get Lua-LaTeX in the. Yeah, it's interesting how it does this, by the way. So it just says it's failing and writes some stuff. Is this anything meaningful? Saying N1 to N2 fill with blue. This will take Z picture, delete. Okay, so if I come in here and I type this in, then I just say begin take Z picture. I'm not super optimistic that it's actually gonna work. Feels like there's some weird stuff going on. Yeah, I'm not super optimistic about this at this point. Hmm. Easy pictures. Oh, yeah, maybe we should do this then. This looks uh okay, also complaining and also created like a whole bunch of junk. I guess it's okay. Like, I mean, I can always debug this offline because like I should have done this, I guess, before. But you know, the graph will look identical to the tutorial, and so I guess like what we can do next is just like it's okay. We can just work with the algebraic representation. Um, so like this. Let's see if we look at ESTG, what does that look like? It's a 5x7 direct simple uh, int graph. Okay, yeah, so it's 5 because there are 5 random variables, and then there's going to be 7 edges between them. And so, how do we print this whole graph though? The variable? Do I just say print line? Does this work? Maybe it's like for so for each sorry, for vertex and ESTG, and then say print line vertex. Should this work? Expression, no method, matching, iterate, collect edges, ESTG. Okay, excellent. Uh, select edges, ESTG. Interesting. So edge 1 to 2, 1 to 3. Oh, interesting. Yeah. Oh, this is really. What is this collect function? Interesting. Okay. Yeah. So just to sort of prove the point, because like we're going to be working with real data soon. I'll draw this out. So if you come in and you say, okay, well, first off, we have x, and then so we have edge 1 pointed to 2. So 2 is w. Yeah, so it's going to be like this, right? So uh, maybe like so yeah, it's going to be like this, like 1, 2, 3, 4, 5, right? And so it's going to say edge 1 to 2. It's going to say 1 to 3. It's going to say 2 to 1. So you see, that's why it had the double connection. It's going to say 2 to 4. It's going to say 3 to 1. All right. 3 to 4. And then 4 to 5. So I just want to show you something else that's interesting. So let's assume, so here, for example, we took 1,000 samples. But let's say we had a lot less data. Like, let's say we could just observe like 5 samples. Like, would this change? Yeah, so with just 5 samples, for example, we have like an edge from 2 to 3, 3 to 2, 4 to 5, and then 5 to 4. So it's sort of like this is sort of an interesting one because like there is sort of a like if you don't know anything about one, you could be led to believe that there's a relationship between 2 and 3 directly. And here it figured it out, but it didn't figure out that 4 had any sort of dependency on 2 and 3. Let's increase the number of samples, like to, I mean, I'm gonna make it a shit ton. Let's hope this runs in a reasonable amount of time. Oh, out of memory. Oh, interesting. Okay, so if you give it 100,000, it doesn't change the result from uh, 1,000. It still seems to believe that this is the same. So that sort of tells us, like, theoretically, I think Moritz mentioned this to me, like, theoretically, you can't do better with more samples. But I mean, let's see, like, when does it sort of like break, right? Like, let's say 500. Yeah, so I mean, 500 seems to be enough. What about 100? I mean, 100 also seems to be enough. That's kind of cool, actually. It's like so few samples and it figures out the whole relationship. 50? 1 to 3, 2 to 4, 3 to 1. Oh, interesting. Yeah, you see. So this is where it starts to break down. It starts to think, okay, well, maybe there's actually a relationship between 4 and 5 as opposed to between, uh, from 5 to 4 as opposed to just it being like one directional here. So it does seem like 100, I think, is the smallest I could find that is reasonable. Um, yeah, and so this speed, for example, is like a sensitivity to, like, if like the higher it is, I think, let's try it out, right? So let's say it's 0.9 instead. Then you're just gonna have a lot more candidate edges versus if you reduce it. The restriction for having an edge will be like a bit harder, so you're gonna have less edges. Um, And so, and also, like, one other thing I want you to notice is that, I mean, let's say this is 1 to 2, 2 to 1, 2 to 4, 3 to 4, 4 to 5. Yeah. So let's say, for example, like we change this to be, uh, I don't know, times 5, for example. Like, I don't expect this should change the results at all. But it does change the results. Interesting. So just because it's a constant, I don't see why this would change anything, but maybe it's because, like, it makes the impact of v disproportional to everything else, and so what ends up happening. Oh, I see what we did. So basically, v gets so big that it doesn't like it doesn't seem like there's any sort of dependency on it from anyone else because this is just so much bigger than what you're getting here. So the way we would fix this is if we said times randoms of n times 0.25. Yeah, just like have to be a much smaller number that you're multiplying with. All right, so let's start trying out some real data at this point, and then uh, or maybe even, like, let's just go a causal inference, Julia, and we can go over the docs a bit as well, documentation. So I mean, yeah, so actually, Moritz already has like some nice examples. So let's make sure we add all the right libraries that we need here. We'll activate our environment again. And then I'm going to add the limited files, linear algebra, and statistics. All right, so this looks like it's working. And so the first thing we're going to do is I want to get the data set. So this is using the NCI 60 CSV. What's NCI 60? So I believe this data set was gone, if I'm not mistaken, but I think we can actually always find it with the web archive. That shouldn't be a huge deal. Oh no, it does work actually. So we're just gonna download it via Julia though. And so if I'm here, I'm gonna say run. Syntax character, this rule contains multiple characters. Oh, IO error could not spawn ht-NuGet. No such file or directory. I mean, it's here though. Oh, I see. Okay. Yeah, it's fine. Like, this is a weird bug actually, because like, oh, you're running wget. I see. I see. No, I forgot the wget there. Yeah, yeah. Okay, fixed. So let's take a look at this thing first, see what it looks like. Okay, it does not look human readable. Um, just a bunch of numbers. Okay, let's try to figure out what some of these numbers mean first off. So first off, I thought I had it, but I had a really nice CSV viewer. Yeah, I had Rainbow CSV. Why is this not working? Okay, install. Okay, so this just helps us figure out like what's like the same color is the same feature essentially. So this lets us figure out like if we're spilling over into multiple lines. I found this really useful when I was working with proteins. This looks gigantic actually. What is the hell is this? Okay, so let's just go to their website and then see what this is about. Okay, parent directory, parent directory. So a fast PC algorithm for high dimensional causal discovery with multiple core PCs. Do they explain anywhere what this data set is, I wonder? Like NCI. Oh, I see. It's a famous data set. Okay. So it's a cancer cell line panel. It's a group of 60 human cancer cell lines used by the National Cancer Institute for the screening of compounds to detect potential anti-cancer activity. It holds cell lines representing leukemia, melanoma, non-small cell carcinoma. It's always, by the way, interesting me more. It's that like most of the like it seems like people have been doing this in medicine for a long time. I guess just because like the causality there like matters for uh like what's a symptom, what's the cause, and where should you do an intervention. I think even maybe the language of an intervention is very natural in medicine. Uh, it's also, I guess, natural in economics, but that they're like it's just a bit more questionable, like whether an intervention actually helps or not. Um, okay, I mean, does it say like columns, for example, cell lines? Use RSA of cell line possible to compare tested compounds. I think a reason is that not all interventions are ethical and possible in medicine. Yeah, that's a really good point. Actually, it's a person, right? It's not just like some software tool. Uh, let's see. So as a leukemia, okay. Okay, so it doesn't seem to say just like number of rows, number of columns, and like what those columns mean. I wonder, actually, does what's it called? Kaggle have them? Kaggle, NIS, NCI. Oh yeah, they do have it. Okay, excellent. So how many columns do we have here? Oh, we have 68,000 columns. I see. Oh, I see. And then each one of these. Okay, I see. I see. So we have 64 possible like types of cancer. Is this what this is about? And then these are all the features associated with it. Interesting. Okay. Provenance is specified. I mean, yeah, I was like, well, why aren't like when's the next white one? It's like here, then oh, this is column 11. Okay, column 1. And this is kind of oh wow, oh, this was the whole single line. I see. I see. So like very extremely high dimensional. Um, okay, I mean, so let's see what more it's got for us. Like, let's check it out. So you read the image data and compute correlation matrices. Okay, let's just do that. Like we can do it within the shell as well. Uh, and ci60.csv read image not defined. Why is it not defined? Add delimited files. Okay, so now if I do this, read. Oh, is it just like open now? No, it's still like what you said in using. Okay, yeah, my bad. It's like switching between Python and Julia just throws me off for this stuff. Usually I forget about them. Okay, so now we have this guy. Okay, great. So, oh wow, so this doesn't look like it has an entire feature set like the other one. So this has like about 1,000 features. And then what is this symmetric doing? I'm assuming it's going to need statistics. Yeah, so using linear algebra and then using statistics. Okay, so what did this do exactly? So compute the skeleton H and separating sets S. Normal is not defined. I thought we got statistics. So using statistics. Let me just do this. So I thought this would be simpler, but we're gonna say example2.jl, and we have this, and then I'm gonna say include example2.jl package.add distribution. Oh, okay. Uh, so add distributions. Okay. Part of the PC. Okay. Yeah, let me skip it. Oh, looks like it takes a while. Ah. Okay. So we can also skip this. And then let's do this. Okay, so we got a graph with 47 node and 135, 39 edges. Oh wow. I guess this, I mean, goes to show you like how actually complicated the stuff gets in medicine. So we're gonna do this. I like this collect edges thing as well. I wish I could have showed you the graphs like more. It's actually put in some work to give me a nice demo. Oh, I see. It's doing these three dots. Like, is there any way to just? I guess it won't matter too much. Damn, I wish we could just get this drawn. It'd be so much cooler. So okay, that's okay. Like, um, the graph draw. Yeah, I'm thinking of doing this basically. Like, just no, the syntax is slightly different. I guess I could hack this together with like some uh like block editing. I need to download this crap. Okay, whatever. Um, but yeah, so this is sort of like the main idea of I will say like just how you get the causal graph. It's like very simple. You just feed it in, like you take in an image. So I wonder that like how come he makes it symmetrical here? Like why does this matter? Because and then also here in terms of the Gaussian test, I notice there's a few differences from the simpler example. So let's put them side by side and just reason through them. Like why is the other one so much simpler? So here, for example, you're taking in a data frame. So that's so here instead it's taking in uh, okay, this dn. There's this Gaussian test. There's this thing, the symmetric matrix, and you're also giving it quantile. So I think what I'm going to do next is I'm just going to actually take a look at this function. Okay, then we're going to go to PCL. Or we could just do this. Like, let me control assert and say PC. Oh, compute to that, PCL, PCL. Oh, okay, this is the full scope of the library. Interesting. PCL. I'm thinking it's a shame because like what I may just end up doing for like a YouTube video is I'll fix the LaTeX thing and then just show this on as many datasets as possible because like actually maybe how it works is complicated under the hood, but just using it is actually really simple so far, and I think this does a disservice to it. Okay, there it is, PCAlg. So runs the PC algorithm for tabular input data using a p-value p to test for conditional independencies using Fisher's Z transformation. What's Fisher's Z transformation? To test hypotheses that about the value of the population correlation coefficient between variables x and y with a variance that is stable. Fisher transformation. Okay. Okay, so I'm just gonna read this as it's like some test that tests like how correlated two of the variables are. And then so it takes a test. Oh, I see. So by default, it takes a Gaussian, like a Gaussian test. But I'm assuming this is sort of a default value because you can change it to other kinds of tests if you want to. And so then this works. It's like one, make sure that I'm working with a table. What are all the columns of this table? What is the schema? How many uh, how many features are in the schema? And then what does this reduce? Oh, I see. Oh, that's actually a kind of a simple idea, right? Like you're basically saying like, what's the pairwise correlation among all the features in the data set? Is it below a certain p-value, which I guess you're drawing, and that's like what the quantile normal stuff here is doing. Uh, and then but there's some sort of multiple dispatch thing going on. Let's see. So you have PCL. Oh, what was I reading instead? The Gaussian test. Um, so this is look like it's doing text using conditional mutual information permutation test. Oh, this is the CMI test. I see. Oh, and then this is plot the output of the PC algorithm. Oh, do you think I can just use this? Maybe it's like, oh, it's also doing a tick Z graph. I see. Okay, let's look at the bigger function, see what's going on there. So the performs the PC algorithm for a set 1 of n using the tests returns a CP-DAG as a digraph. Okay, so 1, you're doing this sort of skeleton, performs undirected PC skeleton algorithm for a set of 1 to n variables using test I, and returns a skeleton graph and separating set. This is cool. I like these graphs and documentation in general. Disjoint sorted. Check if the intersection of sorted collections is empty. Okay. Unshielded triples in the skeleton. Let's look. I mean, let's just maybe look at the algorithm on Wikipedia. PC graph algorithm. Causal discovery. Interesting. What is this? This book. Okay, advanced data analysis. Is this professor? Cosma Shalizi. Okay, I guess we can always I mean, let's do this, right? So I want to just let me do this. I'll come in here. I think it may take like a third session. I may just ask more. It's like offline how this actually works because I need to read all the proper references. Uh, but what we can do is we can just like get some other data sets and then just try to see how they work. And so I'm just gonna follow actually from the test.jl. And I'm gonna, so yeah, let me do this. Okay, so let's see rest, let's say here. So I can remove all of this. Okay, I'll keep this. And then I'm gonna remove all of this stuff. And then df pcl. Yeah, a correlation. Okay, I think we can just do this, right? So now we can try out a bunch of other data sets. Moritz actually shared with me, so awesome causality. So here there's a whole bunch. Let's see, what looks cool? I'm open to suggestions from chat. Twins. What's twins? Oh, interesting. Okay, I think twins kind of looks cool actually. So yeah, like given includes the birth weights and grams of both twins. Causal inference wearing casual. Wait, I'm a bit confused. Causal inference wearing casual. What does that mean? Is there something here about clothes? Let's see. So Amazon, what is this? Um, I don't. I'm kind of into the twins ones. Let's do this. Um, see. So which one is the one? Uh, so this is the one I want. The birth weight. Oh, it's a joke. Oh, sorry. It's just I was like so in the zone. I didn't get it. Apologies. The features which are different between the okay mortality outcome for both birth weights and grams of both twins. Oh, okay. So let's do this. So twin pairs. Yeah. What does this look like? Okay. Oh, so many people online. So if you have any questions about causality, please let me know. We also have in chat like Moritz, who's a causality expert who can answer questions in a much more intelligent way than I can. Um, so yeah, so we're gonna come in here and then instead here I'm gonna say I'm gonna run wget on this data set. Right, so then I'm gonna do compute the correlation meter, and then I'm gonna collect the edges. And I believe this you are not wearing business sport clothes in causal. I don't think I own a suit, but I've only worn the suit for weddings. Like that's the only I think or like a funeral. I think those are the only appropriate contexts where someone should wear a suit. Um, yeah, does this work? No, sorry. So now we're gonna do this, and then so basically we're trying to figure out like if there's any correlations between you're missing out the DAG for the NCI 60 data. Let me check it out. Oh, oh wow, okay. Yeah, by the way, so everyone, so this is the like I'd strongly suggest everyone check out the graph here being shared. Let me let me do this. Actually, I believe it's here.
If you caught the trailers the first time around.
So this is like when we were working over the NCI 60 data set. Like this is what the causal diagram looks like. The hell is this? What? Totally interpretable, guys. Okay, what's going on here? Like, I guess that we are curing cancer, which is like very, very which is challenging. So interesting. So this looks capped, right? Because there should be a few, unless these are tiny. It's like there should be over thousands of nodes here. Like I only see maybe I don't know 20 or 30 here. Oh, unless some were just completely dropped. But this is very cool. So here, so we were doing this, and so now we're doing this twin pairs. We're doing this symmetric thing. Uh, does this work? There's something's going on. Of two twins, their birthdays, and so we want to see if there's some sort of strong causal relationship between the time you're born and your weight. Unless I hope this didn't get confused and is thinking that wait, what's C though? Oh, straight up, my computer crashed. Like the whole thing is hanging. Okay, so I did something bad, I guess. Let's see. Okay, okay, I can get control now. So what's C supposed to be? I think I'm just straight up missing some variables. Should kill this. Kill. Rip. Okay. Everyone like say F for my okay, it got stopped. Okay, excellent. Okay, so what did we do wrong? So I think first off, we forgot to do this correlation matrix. I mean, let's make sure that we have example 2 copied because we know this worked. And so if you go here to example 3, so we're doing all of this, and then we're reading the image. Then we have this. Okay, we removed this for some weird reason. We shouldn't have. Uh, and then we need to just do this. Okay, so this should work now. Like it was just a simple bug. Do we need H or S for any reason? Doesn't look like we do. So now we can just say again here. Come on, Julia, you can do it. Okay, just gonna activate the environment again. And then go back to Julia, and then I'm gonna say include example3.jl. Oops. I forgot the code. Um, so include example3.jl. Wait, so first activate causality. then include sample3.jl. Claim we can close this. Okay, so hopefully this shouldn't crash our computers. But let's see. I wonder why like it just went crazy last time. All right, I guess I can answer questions in the meantime. Like let's just let this do its thing in the background. Um, but yeah, like remember, like we can get these really nice pictures. Where was the one more shared? Here. You gotta admit this is kind of cool, right? Like if you go to like a meeting and you show this, like everyone like has to agree that you know what you're talking about. I guess yeah, like if we just had names here instead of just like the edge numbers, then this would be. I think that's the problem with the NCI dataset. It's not clear what's what, so it's a bit hard to parse this thing without like a sort of uh, table of reference. So no module matching substring. Okay, so I think I can do this. And then we can get rid of this. And now we can just do twin pairs, T, 3 years, same sex, .csv. Okay, now this should work fine. Why is this not working? No method matching substring. Where am I using substring? In line 115. Expression in line 19. Okay, let's take a look. I mean, literally, if I do this here, so where was it? Example 2. I believe this should work fine. Let me say include. Wait, what? Why? Twin pairs T, 3 years, same sex. Why does this need? Because this worked fine just a second. I mean, if I change this back to uh, NCI, right? Like this should work fine, I assume. This looks like it's working fine to me. Like it's blazingly fast too, right? Like this is kind of nuts. So I think like really the issue is maybe with this guy, right? So let's delete this for now, right? And then we can come in here and we can do this again. And I think it's just something with when the multiple scripts are downloaded, it just messed up the names. 3 years. Okay, I'm just gonna give this a simpler name. Twin pairs. Alright, so I can remove all this shit. Twin pairs. .csv. And then I can do this. Twin pairs.csv is not a file. It is a file though. Twin pairs.csv. I see it here. Oh, is it because it has headers? I wonder if it's because it has headers. Okay, well, this is going to be kind of gross, but let's just do this. Oh, and then this is just like line numbers that they have in the data set. Why do you need those? Like, oh, it's literally weights between the two twins. So this should just have, uh, does this fix it? Out of memory. Keeps getting weirder and weirder. So for that out of memory, I'm suspecting it's because of this here. So if I do, how is the block code again? Is it Alt? No. Shift Control? No. Alt Shift? No. Control Shift. Okay, there we are. If I do this, it's gonna take a long time. Yeah, I need some sort of regex script here. Okay, let me pick something else then. I don't want to sit and do parsing now. Let's look at, I don't know, what is this news data stuff? Okay, it needs some weird access. What about this guy? Okay, it looks better. So treatment, factual, counterfactual. Notepad++ would make quick work on that first column. Yeah, like there was a site I used to really enjoy too. Data Wrangler. Yeah, fuck it, let's do it. I shouldn't be scared. It's like, yeah, I'm sure, like, like even like with some vim command this could be done, but let me just do this. So I'm gonna say wrangle. Yeah, exactly. So it only supports 40 column and 1,000 rows. Okay, yeah, that's fine. So this, you drop split. All right. And then you, how do you say, give me the script? I've used this in forever. And then translate. Multiple transpose. Split. Yeah. Yeah. So this, so you do this, and then it gives you like a Python script that does this for you. So check it out. So this is a Python script that would do this data parsing for you. So I'm just gonna have here, I'm gonna say parser.py. So we go here, and then let's open up a new shell. And then I'm gonna say Python parser py, and then I'm gonna pass it in twin var.csv. What do you mean Python's not installed? Oh, because this is the, oh, I see. No module named Wrangler. Install Wrangler. All right, this should take a second. No module named reader. Where's reader? And put install reader. Okay, can I finally do it now? Fuck's sake. Ah. Why is there no module named reader though? And why doesn't this package deal with its own stupid dependencies? All right, so I think regardless though, because this has two features, right? Like we're gonna end up having like two arrows that point at each other. So I can actually already predict that this is just gonna look something like this. Uh, like this is probably just gonna look something like this. So I mean, now that I think about it a bit more, this may not be the most interesting causal diagram. So let's take a look at a couple more and see what else is there. EGGA. What is this? Okay, what about twins? Okay, that's one we saw already. Oh, interesting. Like, yeah, I think this is the one we wanted, right? Like, so it shows like, do they smoke? Did they have kids? Were they divorced? I think this is a much more interesting data set. So let's work with this one. So I'm going to say run this and then this here. And then this is called twin pairs. Boom. Boom. And then let's do Julia. Activate causality. Then we're going to go back and we're going to include example 3 again. Is this crashing again? What's happening? Okay, cool. It's working. We have a data set. Okay, the moment of truth now. Fingers crossed. I think this is gonna crash because of the yeah, like I think because like it needs the columns removed. I think that's where the no method matching substring thing is happening, because it sees a string and then it fails and it just wants to be seeing numbers instead. I think though, like for us, this is really cool. Like the fact that someone would sit and do these studies, like alcohol, cigar, like how many kids they had. Oh, like the race they married. Like wow, so much stuff. Like okay, let's do this. Okay, this may give us the out of memory error from before, and then we're gonna run into the same compiler issue from before. Well, let's see. No method matching float 64 and substring string. Why? We have no strings here. Oh, but there's missing values. I see. I see. So it's not just as easy as just like feeding it the whole thing. Like there is some data pre-processing stuff we need to do, I think. Yeah, you can see these like where there's lots of commas. This is where some data is missing. But this is really cool. And you need to just remove these IDs. Which is like, why would you have these IDs? I don't know. Like, is it new line enough? Let's see. So I think I want to do like one last thing before we call it is I want to just quickly go over the docs again and just see like what's sort of the full set of features. And then we may call it just because I think what I'll do for probably a YouTube video is I'll just have um, like I'll have a way for you to just load in some sort of pre-processed CSV and then show the DAGs with thick. So I'll just need to make sure I have like LuaTech installed. Uh, Otherwise, yeah. So what did they talk about here? So performance. Oh, I see. Yeah, the package could use, I guess, some help with the docs. That's something I could help with. Oh yeah, go for it. Like, I mean, feel free to ask me anything at any point. Like, just feel free to interrupt me. Um, so yeah, so for example, they have an algorithm for deseparation. So that's what I talked about here. Where was it? I thought we did an example. Um, yeah, but it's basically just like a general algorithm to figure out like R2 sets of nodes in a causal diagram, conditionally independent of each other, given some other variables in the DAG. Uh, so this I don't know what this is. The skeleton and V structure. So it looks like this is some sort of subroutine for the causal inference algorithm. This runs like a whole bunch of tests and then gives you the digraph. This looks similar, unshielded, statistics, Gaussian test. Okay, yeah, so the Gaussian test looks like it's a conditional independence test for two variables. Uh, and then compute the partial correlation of nodes, CMI test, KL entropy, divergence, volume of an n-dimensional unit sphere. Okay, so just like some generic ML stuff, the Renier, mutual information. The FCI algorithm has Mark. Hello, this is Mark. Uh, oh, interesting. Like, does this do these pair of edges form a collider? Is this apparent? Is this a triangle? So I mean, yeah, all of this you can inspect as soon as you get the Tix graph, causal inference digraph, V pairs. Okay, so I guess like Chasim 20 200 while you're while you're asking me a question, I'm just gonna download like tech download Windows. Wait, so Lua tech download Linux actually. So okay, so Shawsam is asking. So I started doing my career offensive cybersecurity, working for Big Four. Did that for 4 years, and then did Bitcoin blockchain for 2 years. I'm trying to get into machine learning. So I'm taking Jeremy and Rachel's Fast AI course. After that, I'm reading Ian Goodfellow's book. Any other tips for a new guy? Resources I should tap, things to avoid. Yeah, that's a good question, actually. So I did write a blog post about this. Two blog posts, actually. Let me show you. Because it's like I would say the most common question I get, so that's why I wrote them down. But I would say one at a high level is get good books. Like don't be greedy when buying books because they pay for themselves very quickly. So I would go here and I would buy all the books in the machine learning section here. Just buy all of these; they're all amazing. You'll learn so much. The second thing I would encourage you is to do is that a lot of times in machine learning, there's just like so much going on that you can be doing like perpetual catch up, where you're not really learning anything at all. Like you just think you are because you're reading a lot of stuff. And so what you want to do instead is sort of focus on having like projects and portfolios that you'd like to see at the end of every 2 weeks or so. So I have a blog post there. It's like how to get a great job, where I sort of explain this point of view in a bit more detail. Basically, like, yeah, so this is like another, I'd say, I just sorted down my thoughts here. It's very brief. You're gonna enjoy both. Like, I think, like I said, it's about having books and a portfolio that you can have something to show for it. Because if you're just gonna learn random stuff and just apply for interviews hoping for the best, like, I don't think that's as productive as it used to be. Uh, yeah, so Lua Tech download. I hope that helps. Mm. All right, so where was it? PCL. Okay, and collect the edges. Use data frame. So variables and this. Then let me just look at this error again, just so I remember what it was about. Um, so absolutely does. One of the problems I've been having is I'm getting these information theory textbooks, and while super cool and fun to know, it's just a quagmire of theory, and frankly, I don't think it'll help me as much as on the points on the board project. Um, yeah, so I think the reason you're getting a lot of this advice is maybe you may be asking people that are much older than you for advice. And so there you're going to optimize for the references that they thought were helpful. And so I think actually these books are very, very good. But I would think of it as an and to project. You can't do one or the other. You have to do both. But if you can only have time for one, I think projects are more helpful and more useful. Just because while a lot of companies think they're doing theory, like for the most part, like a lot of work in ML today, I would argue has turned into a sort of like DevOps job where you're using a bunch of libraries, you're running experiments at scale, you're cleaning data in a pipeline. I would say these skills are a lot more valuable than knowing information theory. Even though, full disclosure, I love information theory and I learned quite a bit about it in grad school. I just can't think of anyone I worked with to have actually cared outside of saying they should care because they don't want to say something is useless. They're just being polite. Uh, so activate Causality. Okay, why is this failing? Could not spawn Lua text. Oh, wait a minute.